All right, everyone get ready, because today we're diving deep into electromagnetism.
But no.
Not the basic stuff you learn in school.
Yeah, not at all.
We're going way beyond those equations and really trying to understand a theory that's, well, shaking things up in the world of physics.
That's right. We're looking at this source, electromagnetism, an emergent property of information density.
Okay.
And it's got this radical idea that electromagnetism, it's not a fundamental force.
Really?
Yeah.
Ah.
It's like a consequence of how information is actually structured down at the quantum level.
So we're talking like information, like the ones and zeros, the stuff computers use. How does that have anything to do with, like electricity and magnetism?
It's a tough concept, but think about it this way.
Okay.
The whole universe, it's like a massive ocean of information, right?
Okay.
And this information, it's not just data, it's like the very essence of everything, and it's got a structure to it, a way it's organized.
Okay, so instead of thinking about electrons as these tiny little particles with charge, we're thinking about them as like little bundles of information.
Exactly. The source even calls them like knots.
Knots.
Knots, yes. Like dense knots of information.
Right.
And the more densely packed that information is, the stronger the electromagnetic effects are.
I'm trying to wrap my head around this.
Right.
So how do these information knots make the electric and magnetic fields that we see?
Right, right.
The source mentions like something called coherence shifts.
That's the key to it all. Think of coherence like how organized the information is, right?
Okay.
Like a really coherent system. It's like you walk into a library,
right.
Everything's perfectly in its place.
Okay.
Now, decoherence, that's like someone took all the books in that library and just scattered them everywhere.
Right.
The information's still there. It's just all messed up. It's less useful.
Yeah. So in this framework, are you saying an electric field is made when information becomes more coherent, like it's getting organized, like our library?
Yeah.
And then a magnetic field comes from when it goes towards decoherence, like when it's getting more jumbled up and scattered?
That's basically it.
Okay.
It's like this constant back and forth between coherence and decoherence, this dance where information is like disorganizing itself at this quantum level.
Right.
And that's what we experience as electromagnetism.
Okay. That is wild. So if these information shifts are creating the electric and magnetic fields, then what about, like charges?
Right.
Because we usually think of electric fields as coming from, positive and negative charges.
That's where this gets really interesting, because this source is suggesting that charge itself might just be an emergent property of these coherence shifts.
What?
Yeah, like imagine there's this area of space, and all of a sudden, information gets really, really coherent, forming a dense knot. That super concentrated information, that would create an electric field.
Right.
And we would see that as a charge.
So charge isn't fundamental. It's just a consequence of like information getting super organized.
Yeah, pretty much. And this could explain something we've never, ever seen.
What's that?
A magnetic monopole.
A magnetic monopole. So like a magnet with just a north pole or just a south pole.
Yeah, like an isolated pole.
Right. Magnets always have both.
Exactly.
Right.
And that might be because magnetism, it's not about fundamental charges, but about these shifts in information coherence, like gradients in information density, flowing and changing all over the place.
Wow. Okay. I'm starting to see how this new way of looking at things could really change how we understand electromagnetism.
For sure.
But let's go back to electric fields for a second.
Okay.
The source talks about Gauss's law,
right,
which is all about how the electric flux through a surface relates to the charge inside. So how does that fit into this whole information picture?
Well, Gauss's law is basically saying that the strength of the electric field coming from a charge depends on how much charge is inside.
Okay.
Right.
Yeah.
But in this information framework,
Yeah.
we can think of it as the denser the information knot is, the stronger that electric flux is going to be.
So it's not just the amount of charge, it's like how tightly packed that information is.
Exactly. The information density is key.
Okay.
And this leads to some pretty crazy implications when we start talking about, like, black holes.
Oh, yeah, black holes, they're famous for that crazy gravity they have.
Right.
But they also have these super strong magnetic fields.
Super strong.
So how does this information idea explain that?
Black holes, they're thought to be like the most information-dense things in the universe.
Oh, wait.
Yeah, when stuff falls into a black hole, all of its information gets squeezed into a tiny, tiny space.
So the information density is just off the charts.
That's the charts. And if this framework's right, all that crazy dense information would make super powerful electromagnetic effects.
Wow.
Including the giant magnetic fields we see around black holes.
So they're like giant cosmic magnets powered by all that information packed inside.
That's a great way to think about it. And this might explain why we see other powerful electromagnetic stuff, like quasars and pulsars, hanging around black holes and other super dense objects.
This is really making me rethink everything about electromagnetism.
A big shift.
Yeah, it is. So if charge is like localized information density and electric fields come from these coherence shifts.
Right.
What about magnetic fields? Where do they fit in?
Remember those coherence shifts we talked about?
Yeah.
Magnetic fields might come not from those information knots, but from the gradients in coherence, like how information density changes across space.
So not just where it's concentrated, but how it's spread out and moving.
Yeah, like imagine the cosmic ocean of information.
Right.
But it's got currents and flows.
Yeah.
Those shifts, those are what make magnetic fields.
So it's like a cosmic weather pattern of information density.
Perfect analogy.
Wow. So we've got electric fields from those information knots, magnetic fields from the gradients, and they're both like constantly affecting each other.
And constantly interacting.
It's like a dance, a beautiful information dance.
It is. And this leads to one of the most profound things about this whole idea.
What's that?
Light itself might be a pure information wave.
Wait, hold on. Light, like the stuff we see?
The very same.
How can that be an information wave?
Well, if electromagnetism is all about how information organizes itself,
Yeah.
then light, which is an electromagnetic wave, could be seen as like a ripple of information density moving through the universe.
So instead of thinking about light as, oscillating electric and magnetic fields,
Right.
we're thinking about it as like a wave of pure information.
That's the idea.
That's wild.
It is, but it fits perfectly with this whole information framework.
Okay.
And it opens up some possibilities that are, well, mind-blowing.
Okay, now you've got to tell me, what kind of possibilities?
Well, if light is an information wave, it means everything we see, everything we perceive, it's all just information being sent to us through the fabric of space and time.
So the entire universe is like a giant cosmic internet,
Yeah.
sending information back and forth using light.
That's a powerful way to see it.
Wow.
And it makes you think about, like, the nature of reality, consciousness, our place in all of this.
I'm definitely going to need some time to think about all of this.
Yeah, it's a lot to take in.
But before we get too philosophical,
Right.
let's bring it back down to earth a bit.
Okay.
This source mentioned that different materials, they interact with electromagnetic fields in different ways.
Right.
So how does this information idea explain that?
Yeah. Why are some things good conductors of electricity and others are insulators?
Yeah.
That's a great question. To understand that, we've got to look at how information's structured inside the materials themselves. It's like every material's got its own internal information landscape.
Okay.
It's how the information's organized at the atomic level.
So it's not just the overall information density of something, it's how that information is arranged inside.
Exactly. And that arrangement, it determines how easily that material can respond to changes in coherence.
Yeah.
Like some materials, metals, for example,
Yeah.
they have a very fluid information landscape.
Fluid.
Yeah, their electrons, they can easily shift into higher states of coherence when they're exposed to an electric field.
So that's why metals are such good conductors.
Yeah,
Their information structure allows for the information to flow easily.
exactly. Now, on the other hand, insulators,
Yeah.
they've got a more rigid information landscape.
Right.
Their electrons are kind of stuck, and they resist those coherence shifts,
Right.
which makes it hard for information and therefore electric current to flow through them.
So it's all about how easily a material can handle those information shifts.
That's a great way to put it. And this applies to magnetism, too.
Okay.
Materials that are easily magnetized, like ferromagnets,
Right.
they've got an internal structure that just lines right up with external magnetic fields.
Okay.
It's like their information landscape is naturally magnetic.
And then the stuff that resists magnetization, like diamagnets, they would have an information structure that pushes back against those fields.
Exactly. Their information landscape is less likely to change when those external magnetic fields are applied.
Yeah, this is fascinating. It's like we're looking right into the heart of matter
Yeah.
and seeing this hidden world of information organizing itself.
It's a whole new way of seeing things.
And how that information's structured, it determines how that material interacts with the electromagnetic forces we experience.
That's a beautiful way to put it.
Yeah.
This is just the beginning, though.
Really?
This information way of thinking about electromagnetism, it could totally change how we understand the universe, from the tiniest particles to the biggest structures out there.
I can't wait to explore those possibilities more.
Me too.
But I think for now, we should let our listeners process all of this mind-bending information.
Yeah, that's probably a good idea.
When we come back, we'll go even deeper into what this framework means and how it could lead to amazing new technologies.
Sounds good.
Stay with us.
We'll be right back. Welcome back. Before we took a break, we were digging into how the information structure inside a material shapes its electromagnetic properties.
Right, like how well it conducts electricity.
Yeah.
Or how it reacts to magnetic field.
Exactly. Now let's push that idea even further and look at one of the craziest things this information framework suggests.
Okay.
Superconductivity.
Oh, yeah, superconductivity.
Oh,
That's when certain materials can conduct electricity with zero resistance.
that's the one.
Ah.
And scientists have been trying to figure out how it works for decades.
Yeah.
This new framework gives us a whole new angle. Remember how we talked about coherence being like a perfectly organized library?
Yeah, where all the information's right there, easy to find.
Well, imagine a material where the information is so perfectly ordered, so incredibly coherent, that information can just flow through it, no resistance at all.
So superconductivity is like the ultimate level of information coherence in a material.
That's the idea. It's like those electrons are cruising down an information superhighway, totally frictionless. And think what that could mean for technology.
Yeah, imagine sending electricity across huge distances, no energy loss.
Yeah.
Or building super powerful magnets for things like levitating trains or fusion reactors.
Right, and there's so much more. Superconducting circuits could revolutionize computing, make processors way faster and more efficient. We could build sensors with incredible sensitivity. The possibilities are endless.
That's mind-blowing, but are there scientists actually working on this, like trying to use this information framework to make new superconducting materials? Or is it all just theory right now?
It's still early days,
Yep.
but there are definitely groups looking into it. They're researching how to tinker with the information structure of materials at the atomic level, trying to create those super coherent states that we see in superconductors.
So they're basically trying to engineer the perfect information landscape for superconductivity.
Exactly. It's cutting edge stuff, but it has the potential to change the world.
Huh.
Now let's switch gears a bit and revisit one of the most basic laws of electromagnetism,
Right.
Faraday's law.
Faraday's law. That's the one that says a changing magnetic field can make an electric current, right? Like how generators work.
That's it. And this information framework lets us see Faraday's law in a whole new light.
Okay.
Remember how we were talking about magnetic fields coming from those gradients in information density, those shifting patterns of information?
Yeah, like those currents swirling around in that cosmic ocean of information.
Exactly. Faraday's law tells us that when those information currents change, when the magnetic field fluctuates, it causes a shift in the coherence of nearby information. And that creates an electric field. It's like those swirling patterns make ripples in space-time, and those ripples are what we see as an electric current.
So it's not just magnetic fields pushing electrons around. It's about changes in information density directly affecting the coherence of other information. And that makes the current flow.
Exactly. It shows how connected everything is. Information is like the fundamental language of the universe, and Faraday's law proves how changes in information can have these ripple effects throughout space-time.
It's incredible. Okay, let's talk about another big one, Ampere's law. That's the one about how electric currents create magnetic fields. How does that work with this information idea?
Ampere's law is all about information on the move.
Okay.
Remember how we said electric current is the flow of information, like electrons zipping through a wire?
Yeah, like little bits of information traveling along.
Right. Ampere's law says that when information flows in a coherent direction, it makes a swirl in the surrounding information field, a gradient in information density that we see as a magnetic field.
So those little information packets, they're creating a whirlpool in the cosmic ocean as they move.
Exactly. And how strong that magnetic field is depends on how much information is flowing and how coherently it's moving.
So a stronger current, meaning more information moving in a more organized way, creates a stronger magnetic field.
Precisely. And this brings us back to coherence. The more coherent the information flow, the stronger the electromagnetic effects are.
This is really painting a beautiful picture of how information is behind this whole electromagnetic show. But there's one thing that's been bugging me. We've been talking about electric and magnetic fields like they're separate things, but we also know they're totally linked. They're two sides of the same coin, electromagnetism. So how does this information idea explain that unity? How can we have these separate information knots and gradients, but also this unified idea of electromagnetism?
That's a great question. It really gets to the heart of how this information framework challenges the way we think about physics. We tend to see electric and magnetic fields as separate because that's how they show up in our everyday lives. We can make static electricity without making a magnetic field, for example, and we have permanent magnets that don't create electric currents.
Right. It seems like they can exist on their own. So how do we square that with this idea that they're both expressions of information?
The key is realizing that information itself is dynamic, it's interconnected, it's not just sitting there, it's always flowing and changing. So even when we see something that looks like a purely electric or magnetic thing, there are always these deeper information processes going on, coherence shifts, and gradients interacting in subtle ways.
So those information knots and gradients are always there, always influencing each other, even if we don't always see the whole picture of how they're interacting.
Exactly. It's like watching a dance. You might focus on the individual steps each dancer takes, but it's the interplay between them, the constant exchange of energy and movement that makes the dance beautiful and harmonious.
I love that analogy. So electromagnetism isn't about separate forces. It's about this intricate dance of information, the constant interplay of coherence, shifts, and gradients, weaving together the fabric of reality.
You put it perfectly, and this dance is happening everywhere, from the tiniest particles to the vast expanse of the cosmos.
This is all so mind-blowing. I feel like we've only just scratched the surface of this amazing framework.
We have, but we've laid a good foundation for understanding how this information-based view of electromagnetism can totally change how we see the universe. And in the last part of our deep dive, we'll explore the even crazier possibilities of this framework, including the potential for groundbreaking new technologies and a deeper understanding of reality itself.
Okay, we're back and ready to keep exploring electromagnetism through this lens of information.
We've covered so much already.
Yeah, it's been a lot.
From looking at those fundamental laws in a new way, like Gauss's law, Faraday's law, Ampere's law,
Right.
to thinking about superconductivity, and even reimagining light as a wave of information.
It's been pretty wild, but you know what? This information-centric perspective is really starting to click for me.
Yeah.
It's like we've got these new glasses on, and we can finally see the patterns and connections in the universe.
I agree. It's a big shift, and it could unlock so much, not just about electromagnetism,
Right.
but maybe about all of physics.
Okay, so about those possibilities, what are some of the coolest things we could do with this framework? The source mentioned new energy tech, artificial gravity, even like information-driven propulsion systems.
Those are some of the big ones.
Yeah.
Let's start with energy.
Okay.
If we can really crack the code of information coherence, we could completely revolutionize how we get energy, store it, use it.
We talked about superconductivity before,
Right.
which would be huge.
Yeah, game changer.
But are there other ways we could use information to, like, control energy?
Absolutely. Imagine being able to directly manipulate the information in electrons
Whoa.
to make a current flow without needing any traditional power sources.
Wow.
Or think about storing energy in the coherence patterns of a material, like some super efficient battery.
Wow, that would be incredible. What about artificial gravity? That sounds like sci-fi stuff.
It does, but if we really take this information framework seriously, it might not be so crazy.
Really?
Remember, the source says gravity itself could come from these large-scale differences in information density.
Right.
So if we could somehow create areas of really, really high information density, we might be able to make artificial gravity.
Okay, that's wild.
It would take a deep understanding of how to structure information at a fundamental level, but it's a possibility.
Imagine what we could do. Space travel. Buildings that ignore regular gravity.
Right.
New ways to get around here on Earth. It would be revolutionary.
For sure. Now, information-driven propulsion, that's where things get really out there.
Yeah, the source talked about surfing on waves of information.
Yeah.
What does that even mean?
Well, if we could make controlled coherence shifts in the information structure of space-time itself,
Okay.
we might be able to make forces that push things without needing any fuel or engines.
So we wouldn't be pushing against anything. We'd be like riding these waves of information.
That's the idea.
Warp drive, here we come.
It's a mind-bending concept, and we're still in the early stages of figuring it out.
Yeah.
But this information perspective opens up so many new paths to explore.
This is all so amazing. It feels like we're on the verge of a whole new era of science and technology.
Yeah.
But with all this talk about manipulating information, Are there any ethical things we need to think about?
Absolutely. Any powerful tool can be misused. If we learn how to manipulate information at such a basic level,
Right.
we have to make sure we use it responsibly and ethically.
I completely agree. We need to really think about the potential consequences of these technologies.
Yeah.
And put safeguards in place to make sure they're used for good.
I couldn't agree more. We need to be wise and cautious as we explore this new frontier, make sure these advances benefit everyone.
Well said.
Yeah.
So as we wrap up this deep dive,
Yeah.
what's the one big idea you want our listeners to take away?
If I had to boil it down to one sentence, I'd say, the universe isn't just a bunch of particles and forces. It's this massive, interconnected web of information. And by learning the language of information, we can unlock the secrets of reality.
That's a beautiful thought, and it makes me feel both small and excited about the future.
Me too.
Thanks for joining us on this incredible journey.
It's been a pleasure.
And to everyone listening, keep those minds curious and those imaginations firing. The universe is full of amazing things waiting to be discovered.